Yeah. All right. I thought they're. Are we done? Okay. All right. Welcome back. So, um, we talked about convolutional neural networks, right? Um, Now there was quite a few questions about how to, you know, some of the details of training convolutional neural networks. So today we're gonna take a look into all the factors that might be related to training of a convolutional neural network. There are certain overlaps. So for the ones that are already covered, I'll probably just go fast or just skip through, so that we can spend more time, at, having fun with coding. So without knowing, what each of the hyperparameters, do, and most of the time, tweaking neural network may feel like exactly this, and at the end you give up, right? And but if you understand, what's going on, right, with different components and things like that, it might become actually much easier for you to twig neural networks and then make it eventually successful. So I'm going to kind of walk you through some of the components of the neural networks, and then we'll have a little deeper dive into each of those components so that you have a better mathematical intuition behind what's going on. And then eventually, we will kind of see more professional way of implementing neural network using PyTorch, in contrast to what we have done so far. One thing I want to mention is that a lot of the things that I'm going to be talking about today and later in the second session is that many of this theoretical perspectives, I will wave my hands. Consider this as kind of like architecture. So convolutional neural network or any neural networks, you're sort of like building a building. And when you build a building, obviously you got to understand the basic structural mechanics and things like that, right? F equals to ma. This is what stress strain relationship look like, and blah blah blah. I mean, that kind of theoretical details are important, right, as an engineer for you to design an architecture. But that doesn't mean that you're going to apply that for every single details, right? When you like lay tiles, for example, nobody actually really calculate everything in terms of the stress strain distribution. Even though understanding the basic principles of when the material develops stress and so on and so forth will be helpful, right? So when you listen to this session, and then when you actually get to practice this, keep that in mind. Just one thing I wanted to mention before we get started. So activation functions, sigmoid, 10H, ReLU, those are the top three activation function in terms of the popularity. And then we're going to see, the pros and cons associated with sigmoid, 10H, and ReLU. And then there are many other, variants of, these functions, such as leaky ReLU or squish, and many other things. And we're going to, deduce those and compare the pros and cons. So the historical most popular choice, obviously, is sigmoid. Back in 90s and 2000s, when people were talking about neural network, 99% of the time, it was sigmoid that they were talking about. All right. So sigmoid, I think I mentioned, briefly in very early part of this course, that sigmoid is kind of a smooth approximation of the step function, right? So it looks kind of like a step function, except that it is differentiable at x equals to 0, right? Such that when you do the gradient descent, you don't have to, be concerned about, not being able to what I mean by that is if you look at the shape of the sigmoid function, it is flat pretty much everywhere except for that small region right around zero. So around zero we have some slope, right? And therefore the gradient is not zero. So there's something interesting going on over there. But except for that small range, pretty much everywhere else, we have flat plateaued surface, which means that the gradient is zero. Now, if you have a gradient of zero at the sigmoid node, remember the computational graph that we've been talking about and the backpropagation process? The sigmoid node will almost always have the gradient value of local derivative of zero, which means no matter, what gets passed from the upstream gradient, because we're multiplying zero, no matter what, it's going to spit out zero during the backpropagation process. So that is actually problematic because, right, probabilistically speaking, your data can be anywhere on this, real line, and then only a very small subset of your data will have non-zero gradient, and then everywhere else you'll receive the zero gradient. And that is essentially one of the reasons, one of the main reasons for this thing called the vanishing gradient. So backpropagation is kind of like, telephone game you're playing. You know what telephone game is? It's a children's game where kids line up and then teacher will show a secret message to the kid that is in the front, and then the kids are supposed to deliver that message backward, right? And, during that process, we're basically like, having a kid that cannot hear well or, whatever, right? And unable to deliver the message to the behind. So, because of that, the layers near the input node are not going to receive any gradient. And then remember, gradient equals to update, right? Gradient is what we use to update our model. So the layers that are closer to the output, deeper layers, are going to receive some gradient, and therefore they will update, right? But then the layers that are near the input layer, the shallower ones, are not going to receive any gradient because the gradient, vanishing gradient will give you just zeros. And therefore, they're not going to get any useful feedback, and therefore there's no update. Does that make sense? All right. Actually problematic. Can you guess why? Well, a little hint for you. For today's lecture, whenever I say why, there's a good chance that the reason is gradient. Okay, so here it's the gradient again. Let me tell you why. So we're seeing this equation a lot, right? We're seeing this linear equation a lot throughout this course. Now, what happens to the gradient, not the function value, what happens to the gradient if the input to a neuron, okay, the xj's, is always non-negative? So xj is greater or equal to zero all the time. the gradient vector will have only positive elements. Now, geometrically speaking, let's think about, well, let's first think about the two-dimensional space, right? In a two-dimensional space, what happens if a vector has only positive components? The vector will be limited to or confined to the first quadrant, and then it'll never visit the other quadrant. And that is essentially the problem with, you know, well, that will cause the problem with the gradient descent process, because think about it. This gradient over here, the local derivative over here, okay, is what we're going to use to update the weights. But then because xj is always positive, so all components are positive for the gradient vector, the direction for update is confined to the first quadrant. Or, well, to be fair, because we're multiplying the upstream gradient, maybe, you know, sign may flip, okay? So the first and the third quadrant, but it'll never visit the second and the fourth quadrant. See what I mean? So this is kind of the situation that we're getting. This is kind of the situation that we're getting. The update only happens in this, you know, the directions that are, you know, that falls under the shaded area, and then you never get to, you know, explore or have a gradient vector that is in the third quadrant or the, sorry, the second quadrant and the fourth quadrant. So this hypothetical scenario, let's say your current solution W is over here, and then through the gradient up, you know, gradient descent update, we would like to get to the optimal value, which, you know, let's say lives somewhere here. Okay? So you got to go down like this, but then because you're not allowed to have a gradient in that direction, your best chance will be to have some sort of a zigzag path, and you can still get there, but this is not the most efficient way of, right, searching for the grade, the, you know, the optimal value, right? So with that being said, if, okay, a layer in front of you produce only non-negative values, only positive values, then you are going to be affected by that layer, because that the output of that layer is going to be the input to your layer, right? So if you use sigmoid as an activation function, because the layer that uses the sigmoid will produce outputs that are always positive or zero or positive, then the next layer that uses that as an input will, you know, be confined in terms of the search direction, and therefore it becomes a harder optimization problem to solve. Okay. Now, in this, you know, visualization, we're only considering a two-dimensional vector space. So it's a 50-50, right? You're utilizing at least the 50% of the all possible directions, and then you're discarding the other 50%. So it may not sound like big of a deal. But let's go up to the 3-dimension, where we now have how many sections separated by the axes? 8, right? So out of those 8 sections, right, or octants, the vector is going to be confined to the first octant and then whatever is the opposite. So 2 out of 8. Should we go up to 4D? How many sections in 4D? 16, yes. I guess I'm in India. All right, good. So out of 16 sections, again, we have more or less the same scenario, right? You know, whichever is the first section, right? And then the opposite. So 2 out of 16. And you see the pattern, right? So the denominator is 2 to the dimension of your space, and then the numerator is going to be always 2. So if your dimension goes up, right? If the feature size goes up, then it's basically the confinement, I would say, is 1 over to the n minus 1. So it'll actually exponentially, decrease in terms of the percentage, right? And therefore, even though in this illustration, it doesn't feel like such a big of a deal, but if you go up to a higher dimension, you're virtually having like, very thin, right? Search direction out of all possibilities. Now, one last thing about sigmoid is that sigmoid uses exponential. And in terms of the computational complexity, exponentials are relatively more difficult to compute compared to things like addition, subtraction, multiplication, blah, blah, blah. I mean, it's still not that terrible, but it is heavier than addition, subtraction, multiplication, division, those kind of a deal. Now, this may not sound like a lot, and it is indeed not a lot. So if you just compute one exponential on your, computer on your GPU, then, the difference is going to be in the matter of nanoseconds, or yeah, nanoseconds, I would say. However, if you have a deep model with millions of parameters, or like ChatGPT, trillions of parameters, right? So even for a nanosecond, if you multiply a trillion, right, it's actually a significant difference, right? So in that reason, sigmoid is not very popular nowadays in the context of deep learning. All right. Now, hyperbolic tangent. Oh, before we move on, any questions? All good? Well, if the sigmoid makes sense, 10H or hyperbolic tangent is just a very, so the same exact thing. All right. So by definition of hyperbolic tangent, we have this exponential representation. Okay, so you remember seeing this somewhere from your calculus textbook, right? So by definition, this is 10H. And then you will realize this is essentially just 2 times the sigmoid minus 1. Okay, I'll leave the proof up to you, but this is essentially it. 2 times sigmoid minus 1, right? Because we have the numerator and the denominator the same. So 2 times sigmoid minus 1, and then we basically have the same form. And what that means in terms of the graph shape, graph geometry, 10H is nothing more than just a stretched sigmoid function, and then shifted so that the output is in between -1 and 1 instead of 0 and 1. All right. So out of all problems associated with sigmoid, we still have the issue of this narrow band of non-zero gradient region. We also have the issue of having to compute the exponential, but at least one problem is gone. Right now, 10H can produce some positive numbers, some negative numbers, and therefore what we just discussed, of issue of having all non-negative outputs, at least that problem is gone. But still, because of the saturation zone, hyperbolic tangent is not preferable in deep neural networks. Okay. So sigmoid and 10H, those are no longer used almost Okay. They are still useful every now and then. A good, I guess, example is that, let's say, for some reason you want to restrict the output of your neural network to the range between -1 and 1. Then voila, at least the final output layer can have 10H activation. Right? Or in a similar reason, let's say, you want to confine the output of your neural network between 0 and 1, or 0 and some scale, then sigmoid could be, your choice, at least for the last, layer activation. Now, this is a new one, rectified linear unit, or ReLU, ReLU. ReLU is, on the other hand, more modern way of activation functions. So Krzyzewski et al. In 2012, when they first came up with this thing called AlexNet, ReLU was proposed. So in terms of the definition, ReLU is just a max between 0 and x, which means when x is positive, then ReLU will not do anything. Okay. But when the value of x is below 0, then it'll cut off and then just make everything 0. So in terms of the graph shape, this is what it looks like. All right. Now, the nice thing about ReLU is that as long as, okay, the value is positive, we have always gradient. Okay. So that problem with sigmoid and 10H is gone. And as a matter of fact, this particular activation function was designed and proposed for that particular reason. Because AlexNet was, first attempt to, kind of revive the, deep convolutional neural network, right? So, they wanted to resolve this, vanishing gradient, problem. And, they decided to simplify the activation function like this. But then, by the virtue of having this straight line over there, you'll always, going to have non-zero gradient as long as your input is greater than 0. It is also computationally super efficient. In terms of the actual practical implementation, if you're familiar with numerical analysis, you don't really do max 0x. You just need to, take a look at the sign bit of your variable. So if you're familiar with the floating point representation, if you have no idea what I'm talking about, just believe me, you just need to check one bit as opposed to doing, a complex computation. So it's computationally super, super efficient, even more efficient than like addition, subtraction, those kind of things. Well, I'm not going to talk too much about the neuroscience stuff. I believe this is a little outdated, so ignore this line. And because ReLU, okay, resolves this gradient problem, neural networks with the ReLU activation tend to converge faster. It is easier optimization problem. However, we still have some issues with ReLU, okay, and we're going to be talking about this soon. But this is not zero-centered, or in other words, ReLU also doesn't produce anything non-zero, negative, right? And because of that, the same issue that we discussed during the sigmoid still applies here. And then, even though I said, at least for the, the second half, we have the gradient. The first half over here on the left, we have the 0 gradient. Right? And then if your data distribution happens to fall under this region, then, the neuron will still not get any, gradient feedback, right? Which means, that particular neuron that are unfortunately under that, zone is going to get 0 gradient all the time. And that what we call dead ReLU situation. Okay. So more graphically, this is what dead ReLU situation looked like. So things before ReLU. Half of the space divided by that line, okay, we're gonna preserve the value. We're gonna pass along the value, but then the other half, we're gonna set everything to 0, right? So consider this line over here. I mean, the points that are above this line are the ones that will have the values preserved, and then they're going to continuously produce gradients. And therefore, those gradients are going to be used to, adjust the slope and the y-intercept of this line. Same thing goes for this line and this line. But look at this guy over here. Let's say this part over here, for this neuron, okay, this region is the positive region, and then that region is the negative region. Let's assume. And when that happens, apparently none of these data points are going to give the gradient to this line, and which means this line will not be able to adjust itself anymore. So you get to actually produce a lot of waste. So out of how many million parameters, how many million neurons you may have in your architecture, you may end up having a bunch of dead ReLUs, even from the get-go, depending on how you initialize your weights. And once you stuck in this situation, right? Right. right, sorry, Zoom. That's why you gotta show up in person. Okay. Now this is acting out. All right. So in that kind of motivation, somebody proposed what's called a leaky ReLU. And as the name indicates, it's a ReLU, but a little sloppy, right? So if you look at the, this part over here, now we have a little bit of slope. So problem solved. Yeah. So leaky ReLU tend to have lesser, dead ReLU situation. And then because we now have, leaky ReLU, we have gradient everywhere now. So even if, your data points or your line end up in an unfortunate location, it will still receive some gradient. And then it will still adjust its position. So that's good. The coefficient over here is usually set by the user. So in PyTorch, if you use leaky ReLU, you're going to need to specify the number. This is kind of an arbitrary. So that's the part that I don't like about leaky ReLU. It's kind of nice, but in the meantime, you're adding more hyperparameters. Remember, neural network training is already full of hyperparameters, but you're introducing additional hyperparameter by using leaky ReLU. And somebody felt the same way. So they proposed this thing called a parametric leaky ReLU, where that coefficient is actually learned from data. Okay? So it's kind of a neat idea. However, in this case, you're optimizing yet another set of variables, right? You have a ton of things to optimize. And on top of that, you want to optimize, these little things. So in practice, this is not very popular. ReLU or parametric leaky ReLU is not very popular. Leaky ReLU is used a lot, especially in generative AI models. People tend to use the leaky ReLU a lot. So if you are curious, by the way, one very good way of improving your skill also is by checking other people's code. And really nice thing about nowadays is that when people publish a paper, they publish their source code as well. So you can almost always find a source code and then take a look at their implementation. And you will learn a lot from other people's implementation. So I kind of do that a lot to see how other people's do things differently. So it is kind of my joy to explore other people's implementation. But it seems like a lot of people actually use the leaky ReLU for generative models, but also a lot of other models. Leaky ReLU is pretty popular choice. Now we're talking about the variants of ReLU. So here's another variant, which is the exponential linear units, or ELU. This is a smooth approximation of ReLU. Okay, so somebody probably didn't like the fact that either ReLU or leaky ReLU was kind of sharp at 0, which means that it's not differentiable. So they came up with this exponential linear units. I guess in terms of the characteristics, I'm not going to talk too much about it because at this point you probably can connect the dots and expand what you've already learned to exponential LU. But I don't know. My personal thought is that this is a little too pedantic, because in the computational world, in the real world, there's no precise 0, right? So the chance of you getting into this exact spot where things are not differentiable is very rare. And even if that happens, it's a simple, if and else statement to go around that exception. Okay, you can just assign an arbitrary, gradient value, right? So a lot of, like PyTorch and TensorFlow, they have a treatment for that already, which is simple an if and else statement. So, just for the sake of making things smooth, maybe, this is a little pedantic. However, since this is a physics-aware deep learning course, there are actually the physics applications. We're going to see some cases where ReLU is problematic, and instead things like ELU, exponential linear units, works better. Okay, especially in physics-informed neural networks, which is the next topic that we're going to study, hopefully from tomorrow. We're going to be doing, we're going to be taking derivatives of the whole neural network. Okay, to represent some partial differential equation governing a physics phenomena. And during that process, there's a significant difference, okay, between ReLU and ELU. So we'll get there. But in, I guess, computer vision and more, like medical imaging type of applications, this is not the most popular choice. All right, so too long, didn't read. I guess almost never use sigmoid unless there's a really strong justifiable reason because of the issues that I explained. 10H is good for some cases, like I said. ReLU is probably always a good starting point. So if you have no idea what to do, go with ReLU. It wouldn't hurt. And it works pretty well for the most of the time. So you'll be happy with ReLU for 80% of the time. But in case for whatever reason, ReLU doesn't give you a good result, then PReLU, ELU, those kind of things might be a better option. And in relation to this particular course, physics-aware deep learning, you may want to use something like ELU because the differentiability is the key for some applications. So when we get to talk about that, we're going to revisit this topic. Question? No question? All right. Data normalization. I'm going to be really quick because essentially data normalization, we're talking about the same thing, but slightly from a different angle. Remember this, right? We just talked about it a few slides ago, that, if the input to a layer has all positive values, then, your search direction is going to be confined, right? And that causes a problem. So the input data that is not normalized, okay, may give you that kind of situation. So no matter what kind of physics data you have, it's always a good idea to normalize that data before putting that, the data into the neural network. 99% of the time, all you need is a standardization. So compute the z-score, and instead of the original set of values, use the z-score. For example, if you're working on thermomechanics, you probably don't want to use the Kelvin unit directly, right? Especially if you're studying combustion and things like that, you have like thousands of kelvins, right? And the temperature will never go below zero, right? In Kelvin units. So it's never a good idea to use that as is. Instead, you probably want to set your own scale where, I don't know, room temperature corresponds to -1, 3000 Kelvin correspond to +1 or something like that, and then scale them. So that's really it. That's really all you need to know. In terms of how you do that, you could do the standardization, you could do just simple scaling and shifting. But I guess there's nothing much to discuss over here. Except there's this cool idea called the batch normalization. So batch normalization is a layer that goes into a neural network. So the idea of batch normalization is stemming from this concern about covariance shift. So in the real world, there can be many different data sources. So we actually had this conversation earlier today with some of the faculty members. But if you're doing an experiment or anything like that, I mean, don't assume that everybody in the entire world will be using the same exact set of equipments and same exact set of materials, right? They all use different materials. They all use different equipments. So even for the same problem, the measurement values or the measurement characteristics may vary, right? So different source data will give you different type of distributions. And at the end of the day, the whole point of doing machine learning and all that is to make something useful, right? Make something that's generally applicable, not something that only works in a very specific. So so that is what concerns with the covariance shift. So here in this diagram we have the distribution in the training data set, and then let's say the test data set happens to be slightly off that training distribution. So in that case, your model may not generalize very well. So people have been looking into the ways of overcoming that kind of scenarios, and the batch normalization is one of them. The idea of batch normalization is not terribly hard. What you do is, so whenever a batch of input comes in, you just compute the average of that particular batch. You don't really care too much about the entire data set because, I mean, usually in deep learning scenarios, the entire data set can be like, several terabytes or more. So computing the mean is not even practical. So we're not even going to, care about the entire data set. Whatever, small batch of data that comes in, we're going to compute the average of that, batch as well as the variance of that batch or the standard deviation of that batch. And then using the batch, we're first going to compute the z-score, okay? And then using that z-score, we're going to scale that z-score and then shift it. And then that's basically what the batch normalization layer returns. And then the scaling and shifting parameter, the gamma and beta, those are the parameters that are learned from data. So again, batch normalization layer is a layer that you can add on top of a convolutional neural network. So this is one example how you could use batch normalization layer. So what you know already is, without these yellow blocks, convolution activation, right? And so on and so forth. Or every now and then you may have a fully connected layer, right? Followed by the activation. However, batch normalization can be inserted in between the activation and the convolution, layer, or you don't have to like insert it exactly this way. You can be always creative, and then there are people actually using batch normalization in different layout. But the idea here is, as a result of convolution, right, you get to multiply numbers, right, and then shift them around. So whatever comes into the convolution block, and then what comes out of the convolution block, there will be the shifting of the distribution because we're multiplying numbers, scaling them, right, twisting them, rotating them. So after that shifting happens, batch normalization has a role of kind of bring, that back to some sort of a sweet spot. so that ReLU can do a better job. So remember the dead ReLU situation where the decision line is over here and all of your data distribution is over there, right? Batch normalization sort of learns to bring the distribution back near that neuron, so that the activation function does a better job. Is kind of the idea. Lots of advantages. I think mostly I mentioned already, so I'm not gonna spend too much of a time repeating myself. The role of batch normalization is actually currently in debate in terms of how effective, how useful they are. I personally experienced that for some applications, batch normalization is great. It works, much better than the model without batch normalization. But for some other applications, it just, screw things up. And like many other things in the deep learning community, there's no scientific explanation or anything like that, because deep neural networks are just too complicated to analyze scientifically. But there are some arguments. So in case you're doing a graduate research or wants to know more, there are some papers that you may want to read, and those are the good starting point. But I think for the level of this course, as far as you understand that batch normalization is something that you could do to, in case you expect to have outliers or, out of the distribution samples, batch normalization might be a thing that can help you out. All right, so really for normalization, just remember to normalize your input. And I think for a lot of physics application, that is probably the only thing that you need to do. Yes. Yes. Yeah. Yeah. Well, so usually in practice, you got to set up kind of a separate models. So one, doing its thing, right? Let's say you want to, I don't know, predict temperature or whatever, right? During the machining process. So let the model thing, and then on the side you have an ad hoc model to detect anomaly. So I am usually against of using one model to, detect the main, detection classification task and detecting anomaly, but instead I let the other anomaly detection algorithm to monitor, anomaly, while the other algorithm, focus on the regression task or classification task or whatever. And that model, okay, which is not the anomaly detection, should still adapt, right? I mean, even if, the toolware, for example, that's actually an excellent example. Machining data will never be the same, right? The toolwares and, the vibration happens, and then the data distribution will always shift, right? And during that shift, your model should be able to adjust to that shift, and then, right? So yeah, still there's a need for, adjusting the model according to the shift in data set. Yeah, yeah. Yeah, absolutely. Absolutely. That is a very typical example of why you would need, things like batch normalization. Yeah. Yeah. I mean, even if like people are producing the same stuff, same manufacturing process, same everything, sensors are different, weathers are different. I mean, there's no physically identical, right, setup. So that's why the generalizability. So this one, also, I'm going to be really quick. You just need to remember one thing. The motivation for this is that, okay, so when I mean, we've already done this in PyTorch, right? We initialize W with, torch.rand_n, and then, just for fun, we initialize the, bias with zeros, right? Remember that? The, but why, normal distribution instead of a uniform distribution? I think somebody asked that question during the class. So here's the answer. So for weight initialization, probably the simplest way is to set everything to zero. And especially if you're from, C++ or Fortran background, you always learn to declare a variable and initialize with zero, right? So with that habit, you decide to, initialize all the things to zero, but there's a problem. What happens in this case? And remember, whenever I ask a question today, likely the answer is gradient. Yeah. So when the weight W is set to zero, then all weight values initially will move in the same direction. Okay. So never do this, because obviously, if W is some constant, then the derivative will, right, always be the same, at least at the very beginning. So that's never a good idea. So random initialization is by default the most reasonable thing to do. But if you initialize the random values with two small values, then the weights will, dwindle to zero. So if you start with the small, random weights, then it will kind of, become weaker and weaker and weaker. If you initialize the weights too large, then that's also a problem because, the values may, explode. So you got to find an appropriate size. Okay. And again, the toy problem that we talked about, it was moderate, I mean, it was an easy problem that we created. The values were in a moderate, range. So, we didn't have to worry too much about that. But in real world problems, initialization of weights can be, can have a really huge influence. So this is kind of what I meant. So as you go from left to right, the horizontal axis, we have the hidden layers. So, on this side is the input, and then we go deeper and deeper and deeper. If the layers are initialized properly, multiply some small numbers, so it gets even smaller and smaller and smaller. And when you have a deep neural network, right, it will quickly dwindle to zero. Is kind of the situation here. Um, on the other hand, right, if you have a too large weight values, then what's going to happen is, some input come in, and then that gets multiplied by some large numbers. So the overall distribution gets bigger, and then multiplied by some big number, right, and gets bigger, 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 bigger. and it'll grow exponentially. So to avoid that situation, the guy named Xavier Gloro came up with this initialization method back in 2010. Long story short, this is what you want to do. Okay, so when you do rend n and then initialize w, you want the standard deviation of that w to be 1 over square root of the input dimension. Okay. Now the proof here is that, okay, so the input x is coming into this layer, and then w is what gets multiplied by, right, those inputs to produce output y. Here, for the sake of convenience, we're going to ignore the bias, right? So this is what the neural network does. I mean, a layer of a neural network does. Now, what you would like to do is you want to keep the size of the distribution more or less the same. Or in other words, statistically speaking, you want the variance of x and the variance of y to be more or less the same. Okay, so in terms of the bell curve, you want the variance of x to be the same as the variance of y so that we preserve the size of the distribution. Okay? So that's the motivation. Now the rest is really, some mechanical calculation, that you already, learned from, step 101. Okay, so the variance of y is apparently variance of this entire summation, right? And then, the variance can go into sigma. So, variance of the sigma is, sigma of the variance if, the WIXI are uncorrelated, right? And then that is, n times variance of WIX, XI. And in the meantime, since variance of WIXI is this, again, stat 101. So just look up your stat textbook. I'm not going to go into that. But then, if W and X are not correlated, then, this variance of WIXI is the same as variance of W multiplied by variance of X, right? Which gives us, okay, variance of y equals to n times variance of w times variance of x. And we want this to be the same as variance of x. And then putting everything all together, you get the conclusion that the standard deviation, or the variance of w should be 1 over n, or equivalently, standard deviation of wi should be 1 over square root of n. So that's what Xavier Gloro and Joshua Bengio came up with in 2010. Now, here's one significant, well, not significant, but one kind of an issue here. We didn't consider the activation function, right? So in their work, they actually, stated that we're going to ignore activation functions because that's too difficult to, handle, because like in this calculation, if you have an activation function, then it's going to be a nightmare, right? So they just decided to throw that under the carpet. And then this is what the calculation that they came up with. And then a few years later, he et al. Came up with an alternative strategy, which is 2 times the Gloro initialization. And then their reasoning was that, well, in modern neural networks, we use ReLU. And in ReLU, half the distribution survives, the other half dies. So let's multiply 2. Yeah. It's really that. There's no, signs or anything. And empirically, the He initialization works very well for many of the convolutional neural networks. Okay. So TLDR, what you need to remember is that the whole point of the weight initialization is to make sure that the input and the outputs have more or less the same size of the distribution. I mean, same, variance of distribution, right? And then Xavier or Gloro initialization is the one that, try to enforce that. However, because of the limitation that they didn't consider the activation function, He et al. Came up with the correction to that by simply multiplying the factor of 2. And I believe different libraries actually have different default settings, but I'm pretty sure that PyTorch uses the He et al. Initialization. But there's an option for you to change that if necessary. Dropout, we already done that, so not going to bother to revisit this. Dropout is not even difficult either. So data augmentation, maybe just a little bit because we have cat picture. It's all about stochasticity, and then we're going to see that later. That stochasticity is actually useful for training a neural network that is more robust and generalizable. So that scenario where you have different factories and different sources of measurement, and you want your model to be generalizable, artificially adding noise is a good idea to overcome that situation, as long as the noise is not biased. If the noise is biased, then you're going to shift the model. But so this is obviously the fact that I rotated this does not make this into a unicorn or something else. It's still the same cat. Size, same thing, still the same cat. Stretch, same cat, same cat, same cat, same cat, right? So these are types of the noise that you can add to the data if you're talking about a computer vision problem. Physics problem, maybe, maybe not, right? Because in case of computer vision problems, the absolute pixel values as far as you're allowed, try to rotate, flip, or whatever. So let's say, for example, you're a CFD person and interested in training a neural network to solve a Navier-Stokes equation, and your scope currently is the cylindrical flow. So flipping upside down usually doesn't really matter in that kind of scenario, right? But definitely you don't want to flip left, right, because then the flow direction changes, right? So, keep those kind of things in mind is all I wanted to say. And then, the rest is, really, I guess, your own, discretion. Now, this might be actually a little more useful for physics applications. Again, artificially injecting noise and still. Yes, sorry. I would say so. Yes. Yes. Correct. So, for physics applications, it's hard to say like do this, do not do this, because every situation is different. So that's where, if you're already a domain expert, then, use your own discretion. If you're a data scientist or computer scientist helping, physicists or, mechanical engineers or whoever it is, then it's always, important to consult with them. Because I run a lot of multidisciplinary works, and then I see this kind of, crazy things happening a lot. Like, my CS student, for example, decided to just randomly augment the physics data set by rotating and, I don't know. Um, um, Anywho, injecting noise and label smoothing is another way of augmenting data, and this might be a little more relevant. So, um, like let's say you have some sensor measurement, arbitrary generating some Gaussian noise, and then corrupt your signal might actually be a good thing, during training, because by doing that, you're sort of guiding your model to learn the general trend, not particular ups and downs, right, in the data set. And you can do that on the label. So a lot of data augmentation, methods talk about the input side of the neural network, but the output of the neural network, the label, could also be, added with some noise. So let's say, the classification problem. So what would be a good example? Let's say you're interested in developing a CNN to do some structural monitoring. So the input is some, image of a concrete structure, and then the output is, whether there's a crack or not, right? The ground truth labels are given as 1 or 0, right? 1 means there's a crack, 0 means there's no crack, right? So you're going to rely on human expert to define that. And then, that's going to be the ground truth label to train your model, which is somewhat analogous to what we saw last time, yesterday, right, during the PyTorch session. When you do that, instead of, giving 1 or 0, consider, adding noise to the label. So instead of saying 1, you could give 0.97, or instead of 0, you could do 1 or something like that, by adding a little bit of noise. And this thing, well, this image over here kind of looks like a crack, but I'm not going to confirm it to you. Okay. And from the model's perspective, which is kind of analogous to a student, because of that uncertainty, it'll try to generalize better. It'll try not to conclude, right? It'll try not to jump the gun immediately and then conclude on something. So that's kind of a funny analogy if you think about it, but that makes a lot of sense. I mean, as a student, if a lecture is full of just facts, and then I just confirm facts in front of you by saying, this is A, this is B, this is this, it's not going to be fun, right? The better way of learning is obviously, hey, here's the problem. Why don't you think about it first, right? So there's a little bit of uncertainty in terms of what the outcome is, and then later I can, correct you with, more accurate thoughts and things like that. So, in terms of training the neural network, we're pretty much the same thing. Skip. Yes. So, the gradient descent algorithm is something that we talked about so far. But are there any other or better optimization method? You might wonder. So we're going to be talking about a little fancier, still gradient descent, a little fancier optimization method. So So consider this problem again. We have a loss function. We have a model f, and then for a given input x, f will produce some output, and that output gets compared with the ground truth. And then your goal is to minimize the discrepancy between the model prediction and the ground truth, right? So you're hearing this over and over and over again. Now we have some data set n, right? Data set of a size n. Now, what does it take to evaluate the loss, computationally speaking? Well, let's consider a problem of classifying images. Okay, so you have an image data set. So X is an image, right? Um, and then usually the image classification problem, we talk about a large, large N, right? Millions of images. So we have millions of images and millions of labels corresponding to those images. We also have the model F, right? Which usually have, millions of parameters or billions of parameters sometimes. So in terms of evaluating the loss, what computationally it takes is we need to evaluate the function value n times, okay, at each and every single image x. Agreed? Now, if you have a million images, just computing the loss is going to take forever. In the yesterday's example, we only had 200 samples that we artificially generated. And then those are very simple, two-dimensional vectors, right? So we didn't really care about, all this kind of stuff. But in the real world, just computing the loss function value, let alone, doing the back propagation and all that, is going to take a while. Speaking of gradient, it's even worse. Because if you think about it, you got to do the back propagation. So you need to have the forward propagation by feeding in all the images n times, million times. And then after that, you need to back propagate over each and every image, okay? Because each and every image defines a term in the loss function. Okay? So in terms of evaluating the gradient descent, this is going to be a nightmare. So how do they actually do that? So this is where the idea of stochastic gradient descent come in. Here's just a hypothetical scenario, so don't take it as is. But here's a more rigorous scenario where we compute everything and then compute the gradient and make everything accurate, and then find the optimal, find the rigorous, exact gradient, and then make one step. And then let's say, for So instead of, trying to be pedantic and try to be, rigorous for everything, you could also consider doing something as follows. For each step, forget about computing the accurate loss, accurate gradient. Just take a sample out of million images. So let's say take 10 samples. And using those 10 samples, compute the loss, right? And compute the gradient. And pretend for that moment your n is only 10. You're going to have some gradient. And of course, that gradient is not going to be accurate compared to the rigorous actual gradient as illustrated as the red arrow. But it doesn't really matter, is the argument that I'm trying to make over here. So the direction of the gradient evaluated in that way may not be accurate. And then as a result of not having an accurate gradient, you may wander around a little bit instead of going straight to the target. You may wander around a little bit, and as a result, you may end up spending more steps to get to that point. But each evaluation, if that takes, let's say, 5 minutes only, as opposed to like the full 1 hour, then even after making 11 steps, you still have 55 minutes, and you can converge much faster. Is kind of the spirit over here. So stochastic gradient descent is really about not being perfect, but about getting things done, right? This is actually my favorite motto. Don't try to be perfect, because you will never be able to achieve a perfection. If you're strongly mathematically minded, then oftentimes you try to be perfect, you try to be rigorous. But in real world, I mean, there's no such a thing. Your computer is not able to, express a precise floating point number anyways. So, what's the point of trying to be perfect? And, a lot of times, the result of training a neural network, you will still have a, prediction that is inaccurate, even if the process of, finding that model was perfectly mathematically rigorous. Right? So why bother is kind of the idea. So stochastic gradient descent, like I just mentioned, is an idea of using a subset of the original data set, call it a batch. And then on that batch, you compute the loss, you compute the gradient, make an update, and then move on to the next step. Okay. So that's really just it, SGD. So that's the default setting. Now, building upon this, default algorithm. So in machine learning, we never use the actual gradient descent. We use stochastic gradient descent. So this is the vanilla flavored algorithm, right? And other than the fact that we're using a subsample instead of the entire sample, it's basically the same as the gradient descent. So that's that. Now, obviously, the vanilla flavored algorithm has an issue. One of the really popular issue here is called the long narrow valley. If you're I guess mechanical engineer who took numerical analysis or optimization, you probably know what this is all about. In a nutshell, when you have a gorge in your loss landscape, or the like literally long narrow valley in your loss landscape, where this is the minima that you want to converge to, but then unfortunately you somehow ended up over here, the gradient will point towards the direction of the bottom of the valley as opposed to the actual minima. And initially you will just go straight down to the bottom of the valley, and you basically bounce back and forth without really progressing anywhere. Okay, so it's going to take a while for your optimization algorithm to actually get out of this narrow valley and then eventually converge there. So this is what is called the long narrow valley problem. Another problem with the gradient descent is this local minima. So remember, the analogy that I used for gradient descent was that you're extremely nearsighted person. So your eyesight is terrible. So you only see, your periphery. And then you're trying to, get up to the mountain. And then you may end up having this kind of situation. You keep climbing up a little more and a little more. And then you reach the peak, which turns out to be, right, not actually the peak that you wanted to get to. So, this is still the point where, you have the gradient of 0. So the usual gradient descent algorithm will just stop over there, thinking that this is the global minima, and there's going to be no update, and then give up, searching for anything. So one, really nice way of overcoming that problem is what's called the momentum method. So momentum method is still a gradient descent method where we introduce now the notion of velocity. So the original gradient descent, your current position xt, right, gets updated by subtracting the gradient vector, right? So you're just making displacement directly from where you are. In case of the momentum-based gradient descent method, what happens here is the gradient vector will be used to develop a velocity. So now the gradient is serving as an acceleration instead of the displacement. You see the analogy? And then internally, you store the velocity value. Okay. So with the gradient, you're accumulating velocity. And then the coefficient rho is kind of like friction. If you don't have rho, or set rho equals to 1, then your velocity may explode and then go crazy. So you're giving a friction like that, so that when we get to 0 gradient, then we no longer receive any gradient from the new source, and then with some sufficiently small rho, the velocity will decrease, and then you will eventually converge somewhere, right? So that's how you update the velocity. Once you have the velocity, then that is what is going to move the current solution to its new position, right? So assuming that many of you are familiar with this high school level physics, right? Um, yeah, this is really just a simple tweak that you can make to the gradient descent algorithm. So that's called the momentum method. Now, the long narrow valley situation, what happens if you have a momentum? We saw that if we don't have momentum, it's going to get stuck, right? If we have momentum, the situation is going to be a little better, because as you go down to the bottom of the valley, right, you will develop momentum, you will develop velocity, and then you will kind of go up a little bit to the opposite side of the valley, and then come back down, right? And then you'll have a bigger swing like this because of the momentum, and less zigzag movement because of that larger swing, and a greater chance of converging to the global minima quicker. This situation, if this guy had a momentum, then this guy wouldn't stop over here, but overshoot a little bit. And then after overshooting and then reach to this point, then from the slope of this mountain, this guy will keep receiving the gradient, and then develop momentum towards the top of the mountain again, right? and then be able to go past that local maximum. So, intuitively speaking, momentum method can be, really nice solution to those two problems that I mentioned earlier. Now, another thing is that since we're talking about stochastic gradient descent as opposed to the original gradient descent, our gradients are noisy, erroneous, right? If we have a momentum, we sort of have an effect of canceling out those erroneous, noisy gradients because we're accumulating the gradient in the velocity term. Okay. Recall that in the original SGD formulation, we use the gradient and then forget about it. So it's for one-time use, right? But with the momentum, the previous gradient is going to be accumulated in the velocity term, which has an effect of averaging out the previous gradient with the current gradient. So even if you have noise, by the virtue of averaging, the noise may go away, right, to a certain extent. So that's another bonus in the context of SGD. Does it make sense? Oh, we do that actually. So the stochastic gradient descent, the batch gets sampled, resampled every now and then. So yeah, that's happening anyways. All right, so that is the momentum method. Now, here's another branch of method called the adaptive gradient. Adaptive gradient, so instead of developing a momentum, developing a velocity, now we're steering the direction of the gradient. So we're adjusting the direction of the gradient is what adaptive gradient descent method is all about. And for that, we introduced this scaling factor, which scales the individual component of the gradient. So dx is our gradient. What happens to that dx is we basically multiply some scaling factor to that dx, okay? So that, the scaling factor is an element-wise scaling factor. So for each of the element, we have a different scale. And then, by having different scaling factor for different component of dx, we can have an effect of, steering the direction of the vector, right? That can be quite useful, especially for long narrow valley situation, because you have the gradient that is not pointing directly towards that guy over there, and by having some scale normalization, you kind of perturb the details, but really the idea is to use this element-wise scaling, okay, of the gradient so that you can converge better. So before I move to the next slide, here's kind of the animation demonstrating different kind of characteristics of different optimization algorithms. So the red one, the slow little guy, over there is the usual SGD. And then the green one called momentum, and then the purple one is what's called a Nasterov adaptive gradient, which is basically the same thing as the momentum. So the green and purple are the same family, and then because of the momentum, you can see that it sort of overshoots, but then it quickly backs up and converges to the final solution. The blue and yellow and black are all same family. That's the adaptive gradient, steering. And because of the element-wise scaling, it is sort of noisy like that, but you can see eventually it converged to the global min. Here's another interesting scenario where we have an optimal solution over here. We all started from there, and then the momentum method, green and purple, initially overshoots, right, and then go back down like this. Here's a Pringles chip, right? So we have the settle point. In case of SGD, on top of the settle point, we have the gradient of 0, so SGD doesn't converge anywhere. Momentum initially overshoot and then kind of pendulum motion, and then eventually quickly picks up the downward gradient, and then go down like that. The steering method in this particular situation seems to work the best, right? Because of the steering of the gradient vector, it'll never even touch the settle point, right? So that's kind of the intuition that you need to have. And unless you're a computational modeler, you'll not have a situation where you actually have to implement this. So that's for now all you need to know. Now, if the momentum method and the adaptive gradient method make sense intuitively, here's what's called ATOM, which is all of the above. It's a hybrid between momentum and adaptive gradient. So in a nutshell, again, you don't have to understand the entire thing, but we have the red line, which is basically the momentum equation written with different variables. And then the second line over here is that, element-wise scaling, again, written slightly differently. And then, your solution X gets updated as a combination of the two, is basically the idea. Again, I'm not going to go into the nitty-gritty details. In case you really want to know, the lecture slides are available on GitHub, so encourage you to take a look. But otherwise, as long as you understand the two different branches and then what ATOM is, you should be fine. So here's a brief history of neural network optimizers. Gradient descent is always like the chapter 1, section 1 in optimization textbook, right? And then machine learning people tend to use the stochastic version, the sloppy version of gradient descent. And then starting from there, we talked about the steering method, the adaptive gradient method. We have ATOM. ATOM is basically the combination of momentum and RMS prop. And it, being a hybrid method, it is very versatile, right? It inherits the advantage of momentum, also the advantage of the adaptive gradient. So if you have no idea what to do, ATOM is always the good starting point. And again, in the previous PyTorch session, we implemented the gradient descent ourselves. Atom is available in PyTorch. You don't actually have to worry about the nitty-gritty details. So that's why I emphasized yesterday that as long as you understand, what gradient descent is, and be able to implement the rudimentary gradient descent, everything else will start to make start to be clear, and then the actual implementation will be taken care by PyTorch. Okay. All right, bear with me, almost done. So, putting all the things together, and then, after we take the break, we're actually going to practice using PyTorch. But, a little tips on the learning process and, hyperparameter tuning. This is a very important, I guess, slide that no textbook will tell you, because this is not a rigorous science. And, professors, have this tendency of, not making a record if something is, not scientific, or, if something is inaccurate or whatever. But this is kind of, really useful kind of empirical tips, that might help you jumpstart, training the neural network. So in terms of the step-by-step, procedure, whenever you have a machine learning problem or deep learning problem, pre-process your data. Like I said, you got to have a nice, input value ranging between usually -1 to +1 is what's ideal. So you can do normalization or scaling, and then make sure that the input values are in between -1 and 1 roughly. Okay. Don't ever use like Kelvin, for example, or some crazy large numbers, like gigapascal, for example. You probably don't want to use the pressure values as is. You want to scale them down, right? And then pre-process your data in that way. So that's the very first thing always. The next step is to design the architecture. Okay. And don't be a hero. I've seen a lot of cases, a lot of students where, oh, I learned about the ResNet, I learned about this, and I'm going to just use everything here for my problem. Never do that. Always my recommendation is to start with a linear model, or multi-layer perceptron that has one hidden layer, just a few neurons. Okay. Start from there, see what happens, and then add more details. Like, imagine yourself, painting a picture. You never start, drawing the picture by adding details, right? You start from a rough sketch, right? Really coarse model, and then, gradually improve. So that's the process that you want to make. Now, this is the really important part. Train your model with only small data, okay? And at that point, don't even worry about generalization or whatever. Start with a small subset of your data. See if your model can overfit. Okay. And I mean, you guys learned about overfitting and bias variance, trade-off and things like that, right? So, but even before getting there, just go with a small subset of training data. See if your model can overfit. If your model can overfit, and when I say overfit, like really overfit, can you push the loss to almost 0, or make 100% accuracy with that small data set, right? If you have a small data set, you should be able to do that. If you can, then that's a good sanity check. A good sanity check that your model is capable of learning your problem. All right. If not, then there's something wrong. There's something wrong about your model. And this is an excellent way of debugging that, okay, without waiting too long. Yeah. When you play with deep learning models, always an important thing to remember is you want to create an environment where you can fail quicker. Yeah. If you can fail quicker, you're more likely to discover the problem and make an improvement. If you're ambitious, start with a large architecture, full set of data. What's going to happen is you're likely going to wait for several days for the training is complete, only to discover that, oh, shoot, there's something wrong. It doesn't work. And then you go back, make changes, retrain, wait another days, and then realize there's another problem, and then keep repeat. I mean, that's not going to work. That's never a good way. Instead, go with a really small data. I'm even talking about 10 images, 100 images, something that, you can check with, less than 30 minutes, I would say, or, less than a minute, even better. Yeah. So set an environment where you can, fail quickly and keep failing. You have to fail. You have to fail a lot. And, each time you fail, you might be able to discover some, issues. And then once you develop some confidence that, your model is doing something reasonable, that's when you can, start increasing the number of training samples. So this is very, 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 very important. As a PI, and when I interact with my own grad students, this is always the first thing that I emphasize. But oftentimes, especially the fresh new graduate students are very ambitious. Oh, I'm going to save the world. And then they start with something really crazy. And then after a week, 2 weeks, 3 weeks, I don't get any result from my student. And then I go check, and then the student goes, oh, I'm still waiting for the training to be done. I'm like, no. So start with something, really crappy. But then, once you develop some confidence, then you should start, actual training. Now, there are lots of, things to tweak. The very first thing to settle is, in my opinion, learning rate. Again, this is not science, so some other people may argue otherwise, but in my experience, learning rate is always the first thing to settle. So you want to figure out a learning rate that is adequate. Okay, and again, that's very unscientific term. Adequate learning rate is what you want to find. If the learning rate is too low, then the progression is going to be very slow. If the learning rate is too high, then the loss function values will just fluctuate like crazy or even explode. So it's always a good idea to start with a small number, similar to what we did yesterday. Start with some small number and see if it converges. And if it does, try to push that up a little bit, see if it converges even faster. And then, test how far you can push that up. Okay. So while you're experimenting with the learning rate, you probably don't want to wait until the training is complete. You just run it for a couple of epochs, see how fast the loss function value decrease, right? And then, find the learning rate that, works best for you. Now for learning rate, in my view, it doesn't really matter. You don't need to be too pedantic about learning rate. So 0.01 versus 0.011, there's no virtually difference. So, just change the order of magnitude and, explore in a relatively larger range, and then, quickly settle to a learning rate that gives you a roughly good result. And then the rest of the hyperparameters, okay? Rest of the hyperparameters, including, things may include the model architecture itself, right? In case you use, leaky ReLU or other activation functions, that alpha coefficient could be another hyperparameter. Professor Kana yesterday mentioned the difference between hyperparameter versus parameter, right? We already practiced and know how to identify hyperparameters. So, once you settle with the learning rate, time to tune hyperparameters. So this is kind of the general, advice that I want to give you. Now, when it comes to hyperparameter tuning, this is the visual that you want to keep in mind. So your instinct will lead you to some sort of a grid search. So you have hyperparameter 1, hyperparameter 2, okay? And then maybe write a for loop or something, right? To explore different hyperparameter combinations and then run experiments. Versus, you could also do this, just randomly generate the combinations of hyperparameters and then see what happens for those, hyperparameters. So in terms of the total number of samples, we have 9, the same. But the argument here is that the random search, the sloppier version of search, is a better way of, finding the optimal hyperparameter setting. Because A, not all parameters are equally important. There's got to be some predominant parameter. So like this situation over here, the one in this direction is an important parameter, and then the vertical direction is an unimportant. And if that was the case, you're sort of wasting your computational time for evaluating the 3 important parameters repetitively, okay? Because the parameter 2 doesn't have much influence on the model performance. So practically speaking, you end up, repeating the same calculation 3 times, right? Whereas in this case, you're actually leveraging the computational, resource more effectively, in the sense that all 9 samples, in terms of the, parameter 1 value, they're all in a different location. So even for the same, number of experiment, you get to explore a broader range of parameter values, and then therefore a higher chance of discovering a better hyperparameter. Does that make sense? So if you're gonna, strategically, first of all, don't hard code. So a lot of times, what I see from my graduate students is that, is this being recorded, by the way? I hope my students don't watch this. A lot of times, what happens here is, what happens is, a lot of time they just, write a code in Jupyter Notebook. Something doesn't work, go back and change the number directly, and then run the code again, change the number, and they don't keep track of what they've done. You can relate to this, right? So that's usually what people do. And then as a result of doing that, I mean, you have no record of what happened for what parameter combination. And you just end up wasting a tremendous amount of time just sitting in front of a computer, staring at the monitor, loss function values decreasing. And then, at the end of the day, you feel like, oh, it was a productive day. I debugged my code for 12 hours, but then, there's no real scientific progress there. Instead, try to write a for loop or something like that, right? Where you populate a, hyperparameter combination, right? And then for each of the hyperparameter combination, execute it, using, some structured way. And for each of the execution, make sure that you store the values, right? And the nice thing is, I mean, once you have the, more structured code like that, you can just, deploy it. You can upload it to a, supercomputer, or, run the process on your computer, and let the computer do your work. And you go outside, take a cup of tea or, drink coffee or whatever, right? And come back later. There you go. You have a list of values to compare and you just decide. As opposed to sitting in front of the computer, run the notebook, wait, and then go back, change the number, right? So that's something to keep in mind. How are we doing on time? All right, almost perfect timing. Um, one last thing I want to mention, I think, last thing, is the shape of the loss function graph. So number one, it's always a good idea to visualize the loss function graph. So the horizontal axis is the number of iteration or the number of epochs, okay? And then the vertical axis is the loss function. And always try to plot this. Again, don't do this in a, hard-coded way. Like I just mentioned earlier, write a code to, keep track of the loss function values. And then at the end of the training, let your computer to plot something like this, right? Or if you're more, adept at Python, you could also write it in a way that, this is kind of a real-time update. And by the way, there are some, third-party tools that will allow you to plot this kind of visual in real time as you train your model. So that's always a good thing to do. Now, given that you have a way to visualize the loss function curve, this is very important. Remember, determining the learning rate is the number one thing to do. And if you have a low learning rate, this is going to be what you'll be getting. You'll eventually converge, but you may have to wait way too long. Versus if the learning rate is too high, it will go really quick at the beginning and then kind of saturate or plateau. Or if the learning rate is even worse, then it will overshoot at the beginning and then quickly go up. So if you have any, kind of evidence of loss function going down and then, overshoot a little bit, recover up and then plateau or, just go directly up, then that's an indication that the learning rate is too high. Versus, if things are too slow, then, you'll see something like the blue curve. So your goal is to start from the blue curve, gradually increase the learning rate, how far you can go before the training loss start to overshoot. Now, this is another kind of a typical, very common situation that you may encounter as you train your model, which is that the loss function doesn't decrease at the beginning. And then, after many iteration, all of a sudden it started to go down. Usually the problem is the initialization, the distribution of your input values, the distribution of your weight values. Something is off. Something is off that, the loss doesn't really converge at the beginning. And then it takes time for your optimizer to, pick something eventually and go down. The training curve and the validation curve. So, I mean, this is something that we already talked about, but, always it's a good idea to set some, subset for validation and then monitor its performance as well. So during training, you monitor the training accuracy. So this is kind of a flipped version of the loss. You monitor the training accuracy. So the training accuracy goes up pretty well. So that's good. But then if the set of site samples kind of, plateaus like that, then that's a sign of overfitting, right? And in that case, you probably want to make it, generalize better by adding dropouts, by adding batch normalization, by adding, injecting noises, and so on and so forth. Yeah. So this is really the quick and dirty um, overview of how you can babysit the neural network training. So after we take 30-minute break, we're going to come back here and then we'll see actually how this, gets implemented in PyTorch. And we are going to have fun with some real data finally. So I prepared, by the way, unless you are no, no worries. We'll come back after the 30-minute break. I'll show you the data. I'll show you how to train CNNs using Python.